So I wanted to talk a little bit about an example of how this QPU networking program will develop. So we've talked about the call to action where you see the energy efficiency of the computational quantum computers, how quantum networks are critical to help you scale up and build a fault-tolerant quantum computer. So what would the next year look like in QPU networking? And so I wanted to give a vision of how you network quantum computers with, first of all, heterogeneous qubit platforms, let's say trapped ions. So the key components to that project would be, using a simulator. That's naturally the first step as you're planning a quantum network or you're planning to build a quantum computer. You want to simulate the performance of your individual components. So the qubits, the multiple qubits on the chip, the transducer, the optical fiber. And use the simulator as a design tool to help you make selection of which components to use and how to design and fabricate them. And even if doing a network of QPUs is feasible given the performance of the individual components, and then scaling up to multiple QPUs. And so as an example of one thing that Aliro is working on is we're working on simulating an entangling operation between qubits on distinct separated qubit processors. And we're looking at different modalities, different types of transducers for doing the microwave to telecom and the optical transduction there as well. So the simulator is an important place to start before you start trying to connect components in the lab. Then once you've simulated and you use that to design your quantum network of QPUs, then you will need to run that network, actually operate it, set up the entanglement, operate your gates. And that's going to be a critical collaboration between the QPU manufacturer and a quantum network operator like Aliro. And there you're looking for the orchestrator really to take and transform different quantum devices into a unified, easy to access system that can be managed and run reliably, and develop the networking necessary to really couple together the different QPUs, and then go after applications specifically. So first you have to set up and confirm that you can set up the entanglement, that you can do gates across different QPUs, and then run your circuits for an application specific algorithm that you're going to do, and go from there. And as we network these devices, it's one thing to have a single QPU operating fairly standalone. When you start to network multiple, tens and hundreds and eventually thousands of QPUs, you have to have a scalable network infrastructure, just like we do classically. So it needs to be software defined, it needs to be reliable, it needs to adjust to any changes in loss of entanglement or changes in the photon generation rate. So it's really critical that you're able to have a professional network operation and be able to view and manage and set up the entanglement. And so the vision for how this would progress over a few years as you're networking QPUs, we think about a couple areas. First of all, you need to make sure that you can set up and orchestrate distant entanglement across multiple nodes. Then you need to implement the transduction to convert the frequency from the optical into, let's say, the microwave with superconducting, and you'll have multiple transducers for each of your QPUs. And it'll be critical just to make sure you can set up the entanglement to run those gates and then start to operate some simple circuits. You could say it's a hello world for a QPU network. That'll be an amazing demonstration. My guess is that's going to be about a year and a half away. So not too far. And then once you have gates set up and operating with good fidelity and stability, then running algorithms and applications on this network, right? Multiple QPUs looking to solve a problem and showing that you're going to get a speed up from multiple QPUs and benefit from that. So this is a vision of how that QPU networking program will go.